Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. Well, let's just jump right into some of the top stories of the past week. Our lead story today concerns a bullseye that the Juno spacecraft executed as it went into a perfect orbit around Jupiter. The mission took 5 years at a cost of $1 billion. The spacecraft, which is about the size of a basketball court, sailed 500 million miles to Jupiter. And Jupiter, I should point out, is the third brightest object in the night sky. After the Moon, after Venus, we have Jupiter. And the spacecraft Juno went into a perfect orbit around Jupiter. And there's several things that have to be said about this. First of all, the probe is about the size of a basketball court when you unfurl the solar panels. And it showed that, well, NASA perhaps was exaggerating years ago when it sent plutonium into outer space. The Cassini spacecraft, which went even farther out to Saturn, contained 72 pounds of plutonium. Many people protested that fact because if there was a mishap, a small probability, perhaps no more than 1%, that there would be an explosion on the spacecraft, it would mean that perhaps plutonium would go into populated areas. In fact, NASA even contemplated a worst-case scenario when Disney World would have to be evacuated in case of an explosion involving 72 pounds of plutonium being sent aboard a spacecraft called Cassini. In fact, many critics said that would be the end of the space program. If the American people had a choice between Disney World and the space program, perhaps the American people would opt for the first rather than the second. And if the space program were to endanger Disney World, well, so much for the space program. Well, I think NASA came to its senses because even though it costs more, the Juno spacecraft uses solar power 500 million miles from the planet Earth. We should also point out that Jupiter affects all our lives, even today, at this very moment. In fact, if you hear static on the airwaves, believe it or not, much of the static comes from Jupiter. That's right. Your radio is actually an interplanetary receiver because Jupiter is so radioactive, emits so much electromagnetic radiation, that a lot of that radiation reaches the Earth and creates much of the static you hear on radio. We should also point out that Jupiter is the 800-pound gorilla. It's this gigantic planet, larger than all the other planets put together, and as a consequence, it's a vacuum cleaner, a gravitational vacuum cleaner that sucked in a lot of the debris, the comets, the meteors, the dust, and the rocks that typified the birth of the solar system, making it possible to create the planet Earth. In other words, if it wasn't for Jupiter, the Earth would be pelted every day with meteorites. In fact, there would be a tremendous crater right where I'm sitting here at the City College of New York because of the fact that the solar system today is relatively clean. We look in outer space and we realize that perhaps there'll be another collision with a large asteroid hitting the planet Earth, but on a scale of centuries or maybe millennia. If it wasn't for Jupiter, we would have these collisions perhaps every single day. In fact, astronomers who try to use computers to simulate the creation of baby solar systems in outer space have to have a Jupiter involved, or else life would be impossible because an Earth-like planet would be pelted by asteroids as a consequence. We should also point out that, ironically, we actually know very little about the nature of Jupiter itself. For example, there's a gigantic red spot on Jupiter. It's been stable for centuries since it was first observed by astronomers, but we don't know why. We think it's a gigantic hurricane of some sort, perhaps the biggest hurricane in the entire solar system, but we don't know what drives it, what the energy source is. Also, as I mentioned, Jupiter is quite radioactive. Space probes have to be reinforced as they get closer to Jupiter because of the tremendous amount of radiation that the planet emits, but we don't know why. We don't know why Jupiter is so radioactive and so dangerous to approach. And then we don't know what's inside Jupiter. If you were to slice Jupiter open like an orange, we suspect, though we cannot prove, that first you would see the outer cloud layer. Beneath that, liquid hydrogen, an ocean of liquid hydrogen. Beneath that, perhaps solid metallic hydrogen. And perhaps at the very center, perhaps a rocky core, a remnant of the original birth of Jupiter. Now, this ocean of liquid hydrogen is rather interesting because a previous space probe called Galileo was actually sent plunging into Jupiter years ago, where it actually made a splash in that liquid hydrogen ocean. The Galileo space mission was a predecessor to the Juno mission. However, it was partially crippled. The antenna malfunctioned, and as a consequence, we did not get that much usable information about Jupiter itself. However, we got tons of information about the moons of Jupiter, including Europa. And we know from the Galileo mission that underneath the ice cover of the moon of Europa, a moon of Jupiter, there's probably a liquid ocean. A liquid ocean perhaps much larger than our own oceans. A liquid ocean that could even conceivably harbor life as we know it. However, toward the end of the Galileo mission, it was running out of fuel, and NASA decided to plunge the Galileo mission into Jupiter, even though it was not properly sterilized. Now, to be fair, NASA scientists believe that as the space probe entered the atmosphere of Jupiter, it probably burned up and then splashed into the liquid hydrogen ocean. But we're not sure. There's always a probability that some of the germs left on the surface of the Galileo space mission will survive that and perhaps even proliferate, even though, of course, the likelihood of that is rather small. I should also point out that the Juno spacecraft, when it is at the end of its 2 to 3 year lifespan, it will also be sent plunging into the atmosphere of Jupiter, even though it also has not been thoroughly sterilized as a consequence. We also hope that the Juno spacecraft will be able to resolve many of the lingering mysteries concerning Jupiter itself. First of all, why is Jupiter so different from the other Jupiters we see in outer space? The Kepler spacecraft has identified roughly 2,000 extrasolar planets orbiting other stars, most of them the size of Jupiter. But hardly any of them look like our own Jupiter. First of all, many of them are in highly elliptical orbits, meaning that if there was any Earth-like planet, there would be a collision between Jupiter and the Earth-like planet after a certain point, or the Earth-like planet would be flung into outer space like a small marble. So the question is, why is our Jupiter so circular in its orbit? Pure luck? If it wasn't for that, we wouldn't be here right now talking about this question. Second of all, and this is most puzzling, many of these Jupiters orbit very close to their mother star, comparable to the orbit of Mercury. Now think about that. We're used to thinking of Jupiter, Saturn, Uranus, Neptune as the gas giants, which are really out there in outer space. Billions of miles in outer space for the most part. We think of them as cold and forbidding. However, many of the Jupiters that we see in outer space with our instruments are actually very close, orbit very close to the mother star. So the question is, what happened? A new theory has been proposed, and it's rather heretical, and that is Jupiters can migrate. They can execute a death spiral. They can spiral in because of friction caused by motion within the gas of the solar system. Now, luckily, our Jupiter is in a near-perfect circular orbit and will not collide with the Earth. And second of all, our solar system has been pretty much cleaned out. It is pretty empty. We don't see vast amounts of dust in our solar system. However, the thinking is, in other solar systems in outer space, they are so dusty that there's friction. And as a consequence, Jupiter's begin to execute a death spiral, and that's why they are so close to the mother sun. And again, in those solar systems, we don't expect life as we know it. Any Earth-like planet would, again, be flung into outer space if Jupiter were to migrate closer and closer to the planet Earth. Now, for me, this is personally rather interesting, because when I was in school, I still remember reading my first book about the solar system. And the book said that our solar system is probably average. It's probably normal. It's probably like a garden variety solar system. There are probably other solar systems out there in outer space which have circular orbits with the rocky planets orbiting close to the sun, like Mercury, Venus, Earth, Mars. The gas giants further out, Jupiter, Saturn, Uranus, Neptune, and beyond that, the comet belt. So when I learned astronomy for the first time as a child, everything seemed so simple. All the planets in the universe probably orbit in circles around the mother star, with rocky planets toward the center of the solar system, followed by the gas giants, which are further out, and then comets further out from that. Well, boy, were we wrong. All the books were wrong. We now know that our solar system is the oddball. Most solar systems are highly irregular. Orbits are highly elliptical or oval-shaped. That Earth-like planets are quite rare as a consequence because Jupiters can migrate in those solar systems. So we now realize that much of what we thought about our solar system is actually wrong. And speaking about our solar system, Mars is once again in the news. Many people believe that a mission to Mars may first land on an asteroid, then maybe perhaps land on some of the moons of Mars, and then land on the red planet itself, sort of like taking step by step. Well, then the question is, what are the moons of Mars like? Well, the moons of Mars are rather strange. First of all, the orbits are not quite according to Isaac Newton's laws of motion, leading some Soviet scientists years ago to say that perhaps they were man-made. Perhaps aliens created the moons of Mars as space stations. Well, now we have detailed photographs of Phobos and Deimos, and we realize that they're highly pockmarked, meaning that that's probably the reason why their orbits are not quite according to Newton's laws of motion. They're small enough so that micrometeorite collisions can nudge them away from a perfect Newtonian orbit. However, that leaves open the question, where do the moons of Mars come from? The leading theory that I read about when I was a child is that the moons of Mars probably were asteroids captured by the gravitational pull of Mars. However, that also poses a problem. We can measure the orbits of the moons of Mars very precisely and then run the videotape backwards. Newton's laws of motion are so precise we can either run the videotape forwards or backwards millions of years, and we see that the moons of Mars did not come from a capture. They were not captured by the gravitational pull of Mars. Well, a new theory just came out, which is causing quite a stir, and that is that the moons of Mars originated in the same way that our moon originated. Our moon originated roughly 4.1 billion years ago because of a titanic collision, a collision between the Earth and a Mars-sized planet. And the debris spewed the material for the future moon into outer space. Both the Earth and the moon then coalesced because of Newton's laws of gravity to create the present-day Earth-Moon system. Well, the new theory is that the moons of Mars were also created in the same way. There was a small asteroid, perhaps maybe a third the size of Mars, which plowed into the red planet, leaving a gigantic meteoric basin. And sure enough, on the surface of Mars, we see a huge basin left over from a gigantic collision with an object from outer space. The debris left over from the collision then coalesced into the moons of Mars, just like our moon also coalesced from the impact. Now, these are, of course, just theories, but we can give credibility because we have moon rocks. In fact, they brought back hundreds of pounds of moon rock. In fact, when I was a graduate student at Berkeley years ago getting my PhD, I actually peered into a microscope and saw the surface of moon rocks. And the moon rocks that I saw in a microscope are much different than the rocks we see on the planet Earth. Under a microscope, you could see micrometeorite collisions, craters, inside craters, going all the way down. Now, you don't see that with ordinary rock. Micrometeorites burn up in the atmosphere. They don't hit the Earth, thank goodness. But on the moon, they do, because the moon has no atmosphere. So you have micrometeorite collisions of pebbles, tiny little pebbles that hit the moon and created small microcraters, and then craters inside craters inside craters. And you look at the chemical composition of these rocks, and bingo, you find that they have more or less the same chemical content as the Earth itself. So the Earth and the moon are twins. The moon was not captured by the gravitational pull of the Earth, or else the moon would have a chemical composition quite different. But we think that the moon was literally blown out of the Earth, just like the moons of Mars were blown out of Mars. Also, there's new news from outer space in terms of black holes. Last month, we reported that scientists, for the second time in history, have detected gravity waves from the collision of two black holes in deep space. Now we have an observation that also takes place here on the planet Earth, and we now have a radio telescope with the effective size of the planet Earth itself, detecting the details of a black hole ripping a star apart and gobbling it up. Now, first of all, how can that be? How is it possible that you can create a radio telescope the size of the planet Earth? Well, here's how it works. The larger the radio telescope, the more sensitive, the more accurate it is, because you have more electromagnetic radio waves being harvested by the radio telescope and analyzed. However, waves can be combined with other waves in distant locations. Therefore, if you have a network of radio telescopes around the planet Earth, spaced by thousands of miles, you lash them together, and then you combine the waves by computers so that you get an effective radio telescope the size of the planet Earth. So that's how it works. We lash together individual radio telescopes dispersed across the planet Earth, and then we have a computer that processes the information, combines it as if it were one gigantic radio telescope the size of the planet Earth. Now, why do we want this? This radio telescope would be so accurate, it could detect a quarter on the moon. Think about that, a quarter sitting on the moon. That's the resolution of a radio telescope the size of the planet Earth. So what happens is, scientists then turned this radio telescope toward a black hole 4 billion light years away. And they were able to get, for the first time in history, a detailed analysis of what happens when a star falls into a black hole. This is amazing. What they found first was the star is ripped apart. Some of the matter of the star goes plunging into the black hole, never to be seen again. Other matter orbits around the black hole. But in addition, some of the matter goes toward the North and the South Pole. Now, at the North Pole, we have lines of force which shoot out from the North Pole like a jet. And sure enough, the matter from the ripped-up star, as it approaches the North Pole of the black hole, spirals upward and shoots out like a jet. So think of a top that's spinning such that the top and the bottom of the top spew out radiation. These are called jets, and they are perhaps the most recognizable feature of a black hole. In fact, if you're looking for a black hole in outer space, the first thing you look for is a spinning top such that radiation spits out like a jet from the North Pole and the South Pole. Well, bingo. That's what we have here. For the first time in history, we can actually see a black hole having lunch. A black hole ripping a star apart, shooting the radiation to the North Pole and the South Pole into jets. Now, the ultimate goal of this process is to actually hone in on what is called the event horizon of a black hole. You see, surrounding a black hole, there is a sphere. a sphere whose radius is called the Schwarzschild radius. It is the event horizon. Anything that falls into the sphere never comes out again because a black hole is like a Roche motel. Everything checks in, nothing checks out. One day, scientists may be able to actually photograph the event horizon. It, of course, will be nothing but blackness surrounded by swirling amounts of gas, but that would be a tremendous accomplishment in science once we have the first photographs of the event horizon surrounding a black hole, the point of no return, as predicted by Einstein's equations back in 1915. This is truly an amazing feat using 21st century technology to test a prediction made 100 years ago. Also, bad news on the technological front. Many scientists believe that perhaps by the year 2020, we would see market penetration by self-driving cars into the commercial marketplace. Well, that hope perhaps has been dashed by bad publicity coming from a fatal collision involving a self-driving Tesla motor car. First of all, Tesla Motors is founded by Elon Musk, the same billionaire behind SpaceX and PayPal. So many people thought that Tesla Motors surely would be able to perfect a safe self-driving car. Well, what happened recently was a fatal collision took place. There was a truck that made a typical left turn in front of a self-driving car. The computer on the self-driving car did not recognize the truck as it swerved in front of it. The car hit the truck, and the driver died as a consequence. And there were headlines saying that perhaps this is a setback for self-driving cars. Well, first of all, we have to look at the record of self-driving cars and exactly what happened. First of all, self-driving cars have been driving on our roads for years, and we've had no fatal accidents. We've had some small fender benders, but it turns out it was human error that caused those fender benders. So self-driving cars have been on our roads in the past. So what happened here? You see, there are two basic components to a self-driving car. First is the GPS system, which locks onto satellites orbiting the planet Earth, 3 of them at any given time. And the computer on board your car allows it to triangulate its position given the radio signals from outer space. That's how you are able to know the position of your car to within about 6 inches to a foot. However, there's a second component here, and that is your car has to recognize the position of other cars because these other cars are not connected to your car in any way. Perhaps in the future, all cars will talk to each other, but hey, that's for a future date. The weak link in the self-driving car is the radar system. The radar system that can identify children, toys, dogs, as well as trucks that are in the way. That, in turn, requires pattern recognition. That requires the ability of the car to identify what is in front of it. Now, here is the guess, though we're still investigating this accident. The first guess is that there was glare. Glare from the sun shining on the truck, so that, first of all, the driver was confused, and second of all, the pattern recognition software in the car was also confused, thereby allowing this fatal collision to take place. That, of course, is still a theory. It'll take time to verify this theory. But at the present time, it is a setback because pattern recognition is one of the weak spots in artificial intelligence. We can recognize handwriting. We can recognize people's faces. We can recognize junk for what it is. But computers have a hard time recognizing junk, a hard time recognizing handwriting, a hard time recognizing people's faces because there's so many parameters involved. As a consequence, simple pattern recognition is, of course, possible using computers today. Police, for example, use that to pick out a face in a crowd. But the fine details of recognizing cars in all sorts of unpredictable circumstances still are being ironed out. But it means that there's a challenge for the designers of self-driving car to improve the pattern recognition ability of a car. the second part of Exploration, we're going to rerun a recording with Neil Tyson, my friend, astronomer, director of the Hayden Planetarium, and media personality. So again, in the second half of Exploration, we're going to bring on Neil deGrasse Tyson talking about astronomy and the universe. Welcome. Once again, this is Dr. Michio Kaku, professor of theoretical physics at the City College and the Graduate Center of the City University of New York, and this is the second half of Exploration. And with us today to talk about the world of astronomy is astronomer Neil deGrasse Tyson. He's a director of the Hayden Planetarium. He is a media personality. He hosted the Cosmos series on television. And he's also a figure on radio as well. So today we're going to run a pre-recorded interview with Dr. Neil deGrasse Tyson talking about the stars, the heavens, and his role as an astronomer. The first question for you, Dr. Tyson, is if you're a beginner and you want to look at the night sky via a telescope, but you don't want to buy a toy, but on the other hand, you don't want to spend thousands of dollars on the top-of-the-line telescope, what kind of telescope would you advise a beginner to get?
You know, I get that question maybe 1 billion times a month.
Okay, well, 1,000,001 now.
You're right. You don't want to get a toy because the toys, the cheap telescopes, no matter what they tell you on the box, the problem with the cheap telescopes is they're not only hard to use because they have bad mountings and you aim it at something and you just breathe on the telescope and the mounting shifts where the telescope was looking at and the image quality is poor. So just remove that from consideration. If you're worried about spending more on a telescope, then don't get the telescope at all. Just get a good pair of binoculars. Mm-hmm. And you can get a good pair for anywhere between $30 and $50. And binoculars are great because particularly if you're a kid, you can do more than just look up with them. You can look horizontally with them. Right. And if you go to sporting events and that sort of thing. So binoculars have a tremendous utility that a telescope wouldn't have if you were never going to go beyond the entry level. So beyond that now, I would recommend a telescope. You'd have to spend, I think, at least $100. Mm-hmm. But consider that the telescope doesn't go out of style, and you'll have it for your entire life. So for things that you have for your entire life, $100 actually looks pretty cheap. And some better ones are up around $200 or $300. But what you want to make sure is that you have a sturdy enough mounting to keep a stable image in view. And telescopes get more and more and more expensive depending on how many bells and whistles you add. Mm-hmm. You get up around $1,000. Telescopes have computer-controlled pointing systems. Back in my day, we had to actually know where things were in the night sky.
Now you can be a dummy.
Now you just type it in, you know, and the telescope, it has GPS controllers so that it knows where it is on Earth and knows where to point. So
it's nothing. You just sit it on the floor and it sort of like finds itself, right?
It makes coffee for you. Yeah. So basically, I would say there are a lot of camera shops that not only will be happy to sell you a piece of junk, your average good camera shop will also have the slightly higher level telescopes to sell you. And you want to make sure you have at least a couple of lenses, one to see large objects like the moon, others to see smaller ones where you have to need higher magnification. But so basically it's quite broad, and you might have specific needs. For example, maybe you don't have a car, you have to carry the thing yourself. Well, you know, you stay away from the heavier telescopes. There's some simple needs that you might need have to accommodate simply based on where you're going to take the thing. But I can tell you this: if you happen to have a couple of dollars and you want to get a big, powerful telescope, the drawback is it may be so big that it's hard to take with you to places that you might otherwise be going, and then you don't end up using it at all. Mm-hmm. So try to find the telescope that's big enough. A telescope bigger is generally better. It's one of the few things in life where it's always true. Bigger telescopes.
We won't mention the other parts of life for a second.
Generally are always better. better than little telescopes because they collect more light. If you collect more light, you can see dimmer things in the universe. So a simple telescope, a non-toy simple telescope, you can see the rings of Saturn, the moons of Jupiter, the weather bands on Jupiter. You can watch Jupiter rotate. You can see the craters on the moon. You can watch Venus go through phases. You can see that Mars is red and has ice caps on it. With proper filters, you can see sunspots on the sun in the daytime. You can see fuzzy splotches on the night sky, some of which are galaxies outside of the Milky Way. Others are just regions where stars are about to be born. So you can get pretty far on one of these first-level telescopes. But a larger telescope then will bring much more detail to those fuzzy objects, where you need more light to find out what you're looking at. And you'll see spiral structures and galaxies. You'll see centers of star clusters. With more light, you can see dimmer things. And the worst place to be for any of this is the city. You can make sure you've got friends in the country.
Yeah, right.
Make sure you know the country mouse, you know?
Right. So buy a telescope and a country house at the same time.
Yeah, there you go.
Now, there are two kinds of telescopes. One is the so-called spyglass or refracting telescope, this long tube. And then you also have, of course, the reflecting telescope of Isaac Newton. So how big which telescope would you recommend? And if you get a reflector, how big a mirror would you recommend?
I would say the largest practical sized, that is, kind you can just sort of pick up and take with you, a reflector, is going to be the 6-inch reflector. And it has a 6-inch diameter mirror at the back end, and light comes in, reflects off the mirror, bounces back to a device where you stick your eyepiece. And 6-inch diameter is a pretty good diameter for all things considered. But the reflecting telescopes are, because they're open-ended, dust can get in and you can actually drop things down and scratch the mirror. The other kind, the spyglass-style telescope, which is the more classically proportioned telescope that if you were to draw a telescope sight unseen, it's probably the one you would draw, the kind that pirates use. You know, it's just this long tube with a lens at one end and a lens at the other end, and akin to what Galileo developed. That kind of telescope is a refracting telescope. Of course, it describes what the lens does to the light. It refracts, it bends the light down to a focus. And my personal first telescope was a 2.5-inch refractor. And it's a nice sized telescope, and it can see all these things that I told you a moment ago, the rings of Saturn and craters and mountains and valleys on the moon. But it's a little more rugged. It's rugged. If you've got sort of rugged kids, for example, or if you yourself are a rugged adult, that's the kind of telescope you would sort of haul with you as you went out into the country.
And speaking about the rings of Saturn, during the Yankee game several years ago, it's a famous episode where the cameraman zoomed up and showed the rings of Saturn to millions of New Yorkers who had never, ever seen the rings of Saturn.
That is cool. Well, that's a testament to how good the zoom lenses are today.
Yeah.
Zoom lenses, I don't know the age distribution of your audience, but the old-timers will know there was a day before which there were simply no zoom lenses. And if you look at the old TV camera lenses of the past, they had a selection of lenses on a turret, and they would rotate that to bring a different lens into use. And all of the director's instructions never involved a zoom because there were no zoom lenses. And the number of optical elements to make a working zoom lens is so high, and the number of surfaces that the light passes through is so high that the true solution to that had to await computers to make that work. And so now if you can look at a wide-angle view of Yankee Stadium and then zoom into the rings of Saturn, you got a good camera on your hand.
Right.
That would cost much more than your telescope.
Yeah, much more. And the response was so enormous. So many people had never, ever seen the rings of Saturn. They called in. They thought it was a science fiction movie. And it was so great that the next day, they repeated it because the demand was so great during the Yankee game.
Yeah. Well, we need more of that. Just a reminder that sometimes you got to look up.
Which is, of course, hard for a lot of people.
Particularly city people, where if you look up, it's the pigeons there or something, you know. It's just not a natural thing to do.
You take your life in your own hands when you look up in the city.
And you might step in something, you know. There are all kinds of hazards in the city.
Okay, now let's talk about your early life. Was a telescope there in your early life that propelled you to become an astrophysicist?
Yeah, I mean, I'm a city kid. In fact, I grew up in New York City, where the night sky, like I said, is a kind of a rare commodity. You don't even know it's there, really, most of the time. And my first telescope, actually, my very first telescope was a Christmas gift from my parents.
Is that right?
And that was this 2.5-inch.
How old were you?
Refractor. I was 13. And
that changed your life.
Also, it was not because it was my birthday, and I was just turning 13. And it changed. Well, no, I already knew where I was going, but the telescope empowers you to bring the vision to reality. Because I visited the local planetarium in New York, of course, the Hayden Planetarium. So I'd already been bitten by this cosmic bug, and now I had this hunger, and I had to feed it. And so that first telescope was a refracting telescope, and since I kept growing in my hunger and my thirst, I quickly outgrew that, and then I saved money from walking dogs.
Oh, is that right?
Yeah, in New York, as you may know.
A lot of demand for walking dogs.
A lot of lazy adults who own dogs in apartment buildings. You can't just let them out the back door. That would be a hazardous exercise if you live on the 30th floor of an apartment building. So you pay somebody, and they take your dogs out and you walk them. And in my day, I got 50 cents a walk, and a couple of times a day you'd walk the dog. I had it good back then. It doesn't sound like much money, but I didn't have to clean up after the dog the way people do today.
That's the name of the game, right?
Yeah, that's right. That's why they charge more for it, I think. But anyhow, I used that money to buy my next telescope, which was in fact a 6-inch reflector. And
tonight with the big boys.
I was card-carrying amateur astronomer, and it came with a few lenses. I bought some more lenses. Bought the solar filters, and I was ready. I was ready to take in the universe wherever it would get delivered. And I would haul the telescope to the roof of my apartment building, a 22-story apartment building in the Bronx. And I'm embarrassed to say that I was much older before I realized that the name of the apartment building I grew up in was called the Skyview Apartment.
Was that right?
Because it was just a word with no meaning to me.
Right.
While I lived there, and I looked back and I read the two words Skyview. Yeah, that's what I did up on the roof. So it's fascinating that yes, you can become an astrophysicist even if you are star-starved in the middle of the city.
And also, I understand that you have written your memoirs talking about this. Tell us a little bit about your memoirs.
Well, what happened was I kept getting so many questions about what I did when I was a kid and what I did in high school and college. I said, let me just write this down, and I just hand them the book. I said, read this, call me in the morning. And in fact, my memoir, which in fact had a very first appearance a few years ago, but is now in its new edition that just came out last year, at the end of last year. It's called The Sky Is Not the Limit. And it's subtitled Adventures of an Urban Astrophysicist.
That's a contradiction in terms, right? Like Microsoft Works. That's also a contradiction in terms.
The urban astrophysicist. Well, you got to read it to find out how that contradiction gets resolved. But it chronicles part of what I think a reader might be interested in, how I got to where I am. But I don't then dwell on that fact because I'm principally an educator, and what I do is I share the universe with people, but through the lens that I happen to carry as an astrophysicist, but also as a sort of public person in that realm. So a lot of them are sort of vignettes on how an astrophysicist sees the world around you.
Okay. Well, now let's talk about big telescopes, really big telescopes like the Hubble Space Telescope, which is currently orbiting the Earth. But if things go badly for the Hubble Space Telescope, it may plunge like a meteor, like a piece of space junk from outer space, and who knows, may land up in someone's backyard. What do you think about the accomplishments of the Hubble Space Telescope, and do you think it should be allowed to fall back to Earth?
That's a very rich question, and let me address it a couple of ways, but I'm happy to be brief if you have other topics as well you want to cover. The Hubble telescope, as you may know, just celebrated its 15th anniversary, and there is no telescope that's orbiting the Earth that has that longevity, and that longevity came about, and the belovedness of the telescope in part came about because we were able to fix the thing, to service it, to improve it. As electronics and technologies advance, you go up and swap out the detector, that's the business end of the telescope, and put in a new one. Because really, a telescope is simply a bucket to collect light. And what you put at the focus end, that's up to whatever is the state of your technologies. So the fact that it was serviceable by the space shuttle, by astronauts, meant that the accomplishments of Hubble could accumulate in our hearts and minds far beyond the normal life expectancy of a spaceborne telescope. And so whole generations of people grew up knowing Hubble as their favorite thing, through elementary school into high school and into college. So that in part accounts for the love affair we all have with the telescope, not to mention the striking images that everyone now has as their screensaver for their computer. If you look at the productivity of the telescope in scientific terms, as you know, we measure this by not only how many research papers came out of it, but how many citations those research papers received, which is, on the other end, a measure of how influential that research was. And the Hubble telescope, hands down, is the most fertile scientific instrument in the history of science.
Is that right?
That's correct. If you combine both of these factors, number of papers published and number of citations received, there is no comparison. And so that's extraordinary. I mean, and you wonder, how could anyone say, let's deorbit it? Well, the reason why that came up is there are other telescopes that were on the books, that were ready to be launched and ready to go up and will go places Hubble does not go. That is, scientifically, will tread ground that Hubble cannot tread. And so you're left with this fascinating dilemma. There's the bird in the hand, the working telescope that you know is successful and will continue to make discoveries, and this new technology that's going to go up with a new kind of telescope. By the way, the launch vehicle might blow up on the pad, for all we know, right? And then it's gone. You got nothing, right? And meanwhile, Hubble is deorbiting. So there are complex sort of funding, scientific, and political issues that surround when you turn off an instrument and when you turn on the next one. So right now, up to the minute, at last I checked, the new head of NASA, who, by the way, has all the right pedigree to get NASA out of its doldrums and take us somewhere interesting. He's a physicist, he's an engineer, he managed companies, he's got the spirit of a young person, he's got the maturity of an old person. He's got everything. Like he came from Central Casting.
I see.
Who do you need for NASA to take us in? His name is Michael Griffin. But anyhow, right now, he responded to these sort of battle cries of the turning off Hubble, and he says, yes, let's look into what it takes to save Hubble. But in a limited budget environment, I have to pull money from other places. And so he reached to some of these other telescopes and pulled away the money, not to cancel those missions, but to delay them, which is a softer consequence, right, than actually canceling them. Well, now we have the scientists who are part of those missions complaining, saying, no, this is bad. And so this is the politics of a limited budget.
Well, why don't they take a little bit of money from the International Space Station, which nobody wants, and even President George W. Bush has not expressed much enthusiasm for this bathtub in outer space called the International Space Station, and maybe take a little bit of money from the space shuttle. They cost enormous sums of money for the manned space program.
There are two ways I can answer that. One of them is just since we know we want to go beyond the shuttle and the space station in the new vision for space exploration, why not just turn off the switches now? Just abandon them in place or give them to the Europeans, whatever. The problem is there's a lot embedded in that sort of rolling ball. We have international commitments to complete the space station, so that because we have international partners in this exercise. So the recommendations that exist in the new vision for space exploration, now a year and a half old, those recommendations say we will phase out the shuttle, phase out the space station. In big government, you can't just turn off a switch. You have to you need an exit plan. So you turn them out. I mean, you phase them out. And while you phase them out, you phase in the rest of this vision. And so they are now on a phase out trajectory, a phase out plan to have all their budgets go to zero while we finish the space station. And once the space station is done, the shuttle gets retired. So that's a good thing But you just want that to happen even faster.
Yeah, it's a $100 billion space station, and no one can find a mission for it. What's it doing up there?
Well, that's another interesting
That's a whole other
history.
question.
It was born out of a whole other era. It was conceptually born in the Cold War.
Mm-hmm.
We don't want the commies with space stations over our heads,
right.
Kind of thing.
Mm-hmm.
And then you kind of buy into it, and then it's kind of there, right? And so that's a complicated political history. I'm happy to say that the new vision for space exploration does not have that depth of politics driving it. Mm-hmm. There's exploration driving it. There's economics driving it. The goal and the hope is that it stimulates industries in ways that the stimulation of flight, the investment in flight stimulated associated industries. Mm-hmm. So there's some ambitious plans for it that don't derive from political whim, which I think can be the strength of any project.
Okay. Now let's talk about the search for life in outer space. The Mars rovers have been roving over the surface.
Let's first talk about the search for intelligent life on Earth.
Oh, well, there is none. We know that. That's a subtle question.
That's a whole other program, all right? We'll save that one. But go on, I'm sorry.
Okay, well, Mars, right? Mm-hmm. We've had this fascination with Mars, and Spielberg and Tom Cruise
this summer
are going to scare the pants off us with, War of the Worlds. Mm-hmm. And the question is, well, have we learned anything new? We see pictures of rocks. We see indications of maybe water once floated on the surface of Mars. Anything surprising that caught your attention concerning the Mars rovers?
Well, as you know, Mars has twin rovers, six-wheeling on its surface right now as we speak. And they're on opposite sides of the planet, so that there's always one in view that we can talk to and get the data from. Mm-hmm. And there's always one in sunlight. So that's a clever way to explore the planet. These two rovers. Now, I am an astrophysicist, not a geologist or a geophysicist. So there's a limit to how excited I can get by just looking at rocks.
A bunch of rocks, right?
Right. So, but in all respect to them, they get into their rocks. If any of us have known a geologist, their home is filled with rocks that they found out in the valley and in the mountains and in the, So among this, given this fact, the subset of the rocks that I'm curious about are those that could have only formed in the presence of liquid water. Because the goal of the astrophysicist is not tell me what kind of minerals are there, unless those minerals impact or affect the kinds of questions we want answered about whether Mars once had liquid water. Because on Earth, where there's liquid water, there is life. So we have this, you can call it a bias, but I think it's an okay bias, that the search for life as we know it involves the search for liquid water. So NASA has this mantra, follow the water. And so these rovers had, as one of their primary missions, look for rocks that may have been formed in the presence of water. And, in fact, they found them. So we are jumping for joy at this. And so that helps us shape the next mission to Mars, because we know there's no water on the Martian surface. Where did the water go? It's a big mystery. And most experts in this effort believe the water sunk down into the surface and has now formed a kind of permafrost. And so your next round of missions to Mars are going to have to be able to dig. And so we're going to go to places where we think the water is shallowest and start digging. And so that's the role of these missions in the big picture for our search for life on Mars.
And speaking about digging, in the near future, NASA wants to send a space probe to one of the moons of Jupiter, Europa, which may have a liquid ocean underneath the ice cover. And, NASA does have plans. I've seen some of the animation for it. To dig right through the ice of this moon of Jupiter to access the ocean and perhaps one day send a submarine down there. What are your thoughts? Is that a long shot concerning a liquid ocean under the surface of the ice cover of a moon of Jupiter?
That's currently my favorite plan in the works right now. It's still just sort of being sketched. There's no sort of hardware being committed to that idea yet. But in the minds of creative people, the hardware is getting committed. They're trying to figure out how to do this. There's this moon of Jupiter. By the way, the whole Jupiter system, and it's got dozens of moons. I have lost count. One of those moons is one of the largest among them, discovered by Galileo. In fact, it's called the In fact, it's called, one of the Galilean moons is called Europa. And it is way outside of this zone around the sun where the temperature's just right for liquid water. Earth is in that zone. We're not too close. We're not too far. We're just right. It's Goldilocks. We're just right to have liquid water. You go to Jupiter, you expect everything to be frozen. But you know something? The ice on the European surface is, yes, it's frozen. There are cracks in the ice.
We should also point out that at one point, NASA and the European Space Agency were seriously thinking about sending the Europa lander. The Europa lander would not only just land on the ice cover of Europa, but would send a submarine through the cracks into the ocean underneath the ice cover, and perhaps take photographs, who knows, of microbial life, perhaps things like jellyfish, or perhaps even organisms more complex like fish and squid. However, we should point out that the Europa lander has been delayed, and as a consequence, it's not on the front burners of NASA at the present time. So we don't expect to be able to explore the oceans of Europa anytime soon. However, it's tantalizing to realize that because Jupiter-sized planets are much more common than Earth-sized planets, perhaps we've been barking up the wrong tree. Perhaps the place to look for life in outer space is not on Earth-like planets, but on the moons of Jupiter's. And we think that Jupiter-sized planets are many times more plentiful than Earth-like planets. So in other words, aquatic life that gets its heat from tidal forces from a gas giant, could be a lot more frequent, a lot more commonplace in the galaxy than organisms like us. It's something to think about.